Hello everybody and welcome to the homework helper for section 4.2. Let's go ahead and get into it. In our ready section here, it wants us to connect the zeros of a polynomial with the domain of a function. So when we're connecting the zeros of a polynomial, it's useful to think about what that is. So for 1, 2, 3, and 4, the zero is if we were to have a graph of it, if it were to look like this, the zeros of a polynomial would be where it crosses our x-axis. So here we have a power 3, because we have 3 x's, a power 3 polynomial. So we expect it to cross 1, 2, 3 times. So we're expecting to have 3 zeros from a 3-degree, 3 x's, 3-degree polynomial. That's the fundamental theorem of algebra, is how many zeros we have. Now, when we actually look at this issue, at this problem, how do we find out what our zeros actually are? To do that, we need to think about this as exactly what it is. It's 3 terms multiplying by each other. Okay, so it's a term times a term times a term. You know, A is x plus 4, B is x minus 2, and C is x minus 7. These 3 terms are being multiplied together. These 3 terms are being multiplied together. So what does that mean? That means if any one of these were 0, then the whole thing would be 0. And that would be our 0 on our graph. So if our first term were 0, everything would be 0. If our second term were 0, everything would be 0. And if our third term were 0, everything would be 0. So what would x have to be for x plus 4 to be 0? Well, that would have to be minus 4. Boop. Put that negative sign in there. What would x have to be for x minus 2 to be 0? Well, x would have to be 2. And what would x have to be for x minus 7 to be 0? X would be 7. So negative 4, 2, and 7 would be our zeros in this case. Let me zoom in a little bit. It's a little far away. You can look at the freckle on my arm if you want. There we go. Okay. So with negative 4, 2, and 7 as our zeros, we know that's where it's crossing the x-axis. And so all of these are asking essentially the same thing. Here we would set we'd have to figure out what x would cause this to be 0. We'd have to do it here. This one's a little tricky because it's a perfect square. So because it's a perfect square, what would x have to be? Well, x could actually be 2 things, because 3 squared minus 9 is 0, but also negative 3 squared minus 9 is 0. So there's 2 answers in that squaring. And again here, there may be 2 answers here. Good luck with that. Okay. All right. So for the next section, it wants us to find the domain of each of the rational functions. So this is kind of asking the same thing, but just very, very slightly differently. So we're looking at, instead of it being multiplied as a polynomial, we're looking at it as rational functions. So notice that x plus 4, x minus 2, x minus 7 from problem 1, that's now our denominator in problem 5. So we know that if I plug negative 4 in for x, I would get 1 over 0, which is undefined. I know if I plugged 2 in, I would get 1 over 0, which is undefined. And if I plug 7 in, I would get 1 over 0, which is undefined. So when I have 1 over 0, what I have is I have a hole in my domain. So when thinking about this problem, I know that my domain is not going to include negative 4, 2, and 7. Otherwise, it's going to be all real numbers. Okay? So just think about that and how that creates this issue. And if you want, you can pull this into a graphing calculator to kind of see how it looks like. But essentially what happens here is these become our asymptotes. So without actually graphing it, I know that if I were to graph it, at negative 4, at 2, and at 7, I would have some sort of asymptote that would reflect this. So I don't know exactly what it looked like. Maybe it looks something like this, and then maybe it's something like this, and something like that. I actually have no idea what it looks like, but that's what I would expect it to look like, is to have some sort of asymptote where it becomes 0. Okay, let's moving on to the set piece. Now for the set piece, it wants us to practice transformations on rational functions. So when looking at this, we've done some transformations with parabolas and with some exponential equations before, but what does it look like when we're doing a transformation with a rational function? Well, when we're doing it with a rational function, it's actually going to behave kind of similarly, right? Where we're going to have y equals a over x minus h plus k. Okay, where a is our stretch, the speed at which it goes up and down. H is going to be our movement along our x-axis, so it's going to be our back and forth, and k is going to be our vertical movement. Okay. So for this one, our vertical asymptote, our up and down, is still going to be 0, right? Because our base form has it as 0. Our asymptote's at 0. So this is just going to be y equals 0. Our horizontal asymptote is going to be 0. Y equals 0. Our domain is going to be, our domain is the set of all real numbers that are not 0. That's like the fancy way of saying it. Our range is the set of all real numbers that are not 0. Okay, that's it. Let's look at this here, though. So this is going to be 3x plus 2. So that means plus 2 is our k. That's going to be our up and down movement. So normally we expect a rational function to look something like this in the blue. But because we're going up 2, we're going to essentially take this graph and slide it up 2. So instead it's going to look something like this. Like that. Because now we have a new asymptote. Our horizontal asymptote has changed. Our vertical asymptote is going to remain the same. That's going to remain, this should have been x equals 0. X equals 0 is still our vertical asymptote because it's our y-axis. I messed up on that one. But our horizontal asymptote is now that green line, and that's going to be y equals 2. And we can see it right there. It's our k. So our horizontal asymptote, to generalize, our horizontal asymptote is always going to be y equals whatever that k value is. And then it's also worth thinking about, if we were to subtract a number here, that our vertical asymptote would always be y equals h. Okay, that's just to generalize it. So when we're looking at the other problems in this, that's exactly what happens. It does ask us to graph on the other page. So this is actually kind of confusing because this graph on the next page corresponds to number 9, and this graph on the next page corresponds to number 10. So just be mindful of that. So here you see I had my asymptote up at 2, 2, 2, 2, 2, 2, 2, 2. So that's how I would end up graphing this. So it would probably look something like this. It would probably look something like this. And that's how we would do all of these. Okay. So be mindful of that. Let's look at number 11 just to get our brain around it real fast. Let me zoom in just a little bit more if I can. So we have an h of 3. So before I even start graphing it, I know that I have a vertical asymptote at 3. I know that x equals 3 is a vertical asymptote because 3 minus 3 would be 0. I would divide by 0. That's undefined. So again, even before I start graphing it, I know right here at 3, I am going to have an asymptote. Just like so. Okay. I don't have a k, right? There's no number there, so I know that there's an invisible plus 0. So I know that my horizontal asymptote is y equals 0. So before I even start graphing it, I know it's going to look like this. Just like so, in the green. Okay. So I have the basic shape. Now I have a 5 as my stretch, but also a negative. So before I start plugging in points for something like this, I know it's going to be the opposite of what I expect. So normally I expect it to move like so. I expect it to move in this quadrant like so. But because it's going to be negative, it's going to be the opposite. So instead it's going to be something like this. And normally I'd expect it to be in this quadrant, but because it's the opposite, I know it's going to be something like this. Now, I didn't do actual points when you're doing this yourself. I want you to figure out what those actual points are. Numbers worth plugging in would be something like 2. When we plug 2 in, what do we get? We get negative 5 over 2 minus 3. 2 minus 3 is negative 1, so negative 5 over negative 1, that's 5. So I know at 2, I'm at 1, 2, 3, 4, 5. I know that's an actual point that's going to be on it. So test those points, see how it behaves, and go from there. All right, finally, we're at the go piece. All right, so for this one, it says use the given root to find the remaining root. So this is some stuff from last term, or I'm sorry, last unit. Maybe it was last term for you, maybe it wasn't. But this is from the last unit where we know one of the zeros. So when looking at number 14, if I know that x equals negative 1 is one of the zeros, I know that one of my terms was x plus 1, right? Because negative 1 minus 1 would be 0. Ooh, let me use a darker pen. This isn't showing up very well. X plus 1 is one of my terms. And so I know that this is a power 3 polynomial. So when I'm done with everything, I know that if I were to write this as the roots, it would be x plus something, x plus something, x plus something. And I know that 1 is one of my roots. I need to find my other 2 roots. Okay? Easy enough. So how do we actually go about doing this? One of the ways we can do this is just with classic long division. So when I'm doing this with long division, I know I'm taking x plus 1 and I'm putting it into all of this. X cubed minus x squared minus 17x minus 15. Okay. So to do this now, what I look at is I look at my leading term, which is an x, and I ask myself, what do I have to multiply x by to get x cubed? And I have to multiply it by an x squared. So I multiply it by x squared. And I'm lining up my powers. X squared times x is x cubed. X squared times 1 is x squared. And now I subtract. X cubed minus x cubed is 0. That's why I did it. Negative 1 minus 1 is negative 2x squareds. Okay. Now I can bring down my next term, minus 17x. What do I have to multiply x by to get negative 2x squared? I need to multiply that by negative 2x's. That becomes negative 2x squared. That becomes negative 2x. I now need to subtract. Negative 2 minus negative 2 is 0. Negative 17 minus negative 2 is negative 17 plus 2. That's negative 15, or x. Okay, I now bring down my minus 15. What do I have to multiply x by to get negative 15? I have to multiply it by negative 15. Negative 15 times x is negative 15x. Negative 15 times 1 is negative 15. And it zeroes out. Okay, so right here, I know that I've factored it down just a little bit, where I know that x plus 1, given the root I already had, times x squared minus 2x minus 15 is a more factored form of my original equation of x cubed minus x squared minus 17x minus 15. Great. Now what do I do? Well, I'm getting closer. All I have to do now is factor down my quadratic, my x squared minus 2x minus 15. To factor this out, x squared minus 2x minus 15, this one isn't terribly complicated. We can use this one using the x method. Okay, we're looking for two numbers that add to negative 2. They add to negative 2, but they multiply to negative 15. What two numbers do this? Well, what two numbers multiply to negative 15? Negative 15 and 1 are two numbers, but if I add them, I'd get negative 14. Let me put that on screen. Negative 5 and 3 would multiply to negative 15, and when I add them, I get negative 2. So I know that negative 5 and 3 are my factors. So I know I can rewrite this as x minus 5, x plus 3. So this simplifies even further. This simplifies even further to be, I'm going to write this up here, x plus 1 times x minus 5 times x plus 3, which finally means I can get the root of x equals negative 1, that was given to me, x equals 5, and x equals a negative 3, as those are what would cause this to be 0. So now I have all my roots. Complicated, right? Long division, hard way. There is an easier method. It's a little bit more intricate though. And it's called synthetic division. So let me go over synthetic division real fast. Synthetic division. Okay, so to do synthetic division, what we do is we're given one of the roots. So we start by like drawing a little platform like this. Okay, it's like a big old L. And we're going to write our coefficients here. So my coefficient on x cubed is 1, the number that multiplies it. My coefficient on negative x squared is negative 1. My coefficient on x is negative 17. And my constant coefficient is negative 15. Okay, so just writing these numbers out. Then I'm going to write down the known root. And the known root, let me slide that over so you can see it. The known root is negative 1. Okay, so here's how synthetic division works. We start by just bringing down our first number. So I'm just going to bring down the 1. Just every time, just take that first number, bring it down. Now I multiply. Negative 1 times 1 is negative 1. Now I add. Negative 2. Now I multiply negative 1 times negative 2 to get 2. Now I add negative 15. Now I multiply positive 15. Now I add 0. Okay. Now these might look familiar. 1, negative 2, 15. Well, those are the coefficients we ended up with here after our long division. And so synthetic division is a way of speeding up that long division. Now all we do is we lower our power. This was originally an x cubed. Now it's an x squared. This originally was an x squared. Now it's an x. This originally was an x. Now it's a constant. And this was our constant. We don't have it anymore. It's our remainder. And it's a remainder of 0. So essentially, synthetic division allows us to take this whole step of doing long division and do it much more quickly. So now we're able to have a more manageable or a quicker way of figuring out what factor is left over here. Then once we have this, x squared minus 2x minus 15, we can use that classic x method, what two numbers add to negative 2 and multiply to 15. We know that's going to be negative 5 and 3, and then we can solve from there. And those end up being our factors. Boom, 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 boom. Okay, that's all of that. Go ahead and battle with this. I know that this part here, the finding the roots and factors of polynomials, is probably going to be the most challenging. So this is one where you really need to keep an eye on where are your stuck points. Figure out which of these steps, because there's a lot of steps involved here, which of these steps are the ones that are giving you a hiccup, which are the ones giving you pause, so that we can clarify that and work through that. So let me know whatever it is you need, and I'll see you next time.